The asteroid belt represents one of the most fascinating and informative regions of our solar system, providing crucial insights into the processes that shaped our cosmic neighborhood approximately 4.5 billion years ago. Located between the orbits of Mars and Jupiter, this region contains millions of rocky bodies that serve as preserved remnants from the solar system's formative period. These ancient objects range from dust-sized particles to dwarf planets several hundred kilometers in diameter, collectively forming a vast library of information about the conditions and processes that existed during the solar system's earliest epochs. The relationship between the asteroid belt and solar system formation is multifaceted, involving complex gravitational interactions with Jupiter, resonance effects, and early dynamical processes that prevented this region from forming a full-sized planet. Recent scientific research has substantially advanced our understanding of this relationship, revealing how the current state of the asteroid belt provides evidence for specific models of planetary formation and migration that occurred billions of years ago. The asteroid belt occupies a relatively well-defined region of space located between the orbits of Mars and Jupiter. Specifically, this region begins at approximately 2.2 astronomical units, AU, from the Sun, and extends outward to about 3.2 AU, effectively creating a boundary that separates the inner terrestrial planets from the outer gas giants. In more relatable terms, the asteroid belt is positioned approximately 330 million to 480 million kilometers from the Sun. From Earth's perspective, the belt is situated between 1.2 and 2.2 AU away, making it our relatively close cosmic neighbor when compared to the outer solar system. This strategic location between the inner and outer planets is not coincidental, but rather the result of specific gravitational dynamics that shaped our solar system's architecture. The belt takes the form of a gradient ring orbiting the Sun, with its density increasing toward the center before fading in its outer regions. Despite its name suggesting a crowded field of closely packed objects, the asteroid belt is actually an incredibly sparse region of space. The distance between individual asteroids is vast, typically around 600,000 miles, which is why spacecraft can navigate through the belt without significant risk of collision. This substantial spacing between objects provides important evidence against some formation theories while supporting others, particularly regarding the belt's origins and evolution over time. Within the asteroid belt exists a remarkable diversity of object sizes, from microscopic dust particles to massive dwarf planets. Currently, hundreds of thousands of asteroids have been officially cataloged, though scientists estimate that millions or possibly billions remain undiscovered, particularly among the smaller size classes. Approximately 0.7 to 1.7 million asteroids possess a diameter of at least 1 kilometer, while around 200 asteroids are known to exceed 100 kilometers in size. This size distribution follows a power law, with the number of objects increasing exponentially as size decreases, reflecting the fragmentation processes that have shaped the belt throughout its history. The four largest objects in the asteroid belt are Ceres, Vesta, Pallas, and Hygeia, with Ceres standing as the unquestioned giant of the region. With a diameter of approximately 940 kilometers, Ceres is so large that it has been reclassified as a dwarf planet, the only object in the main asteroid belt to achieve this designation. Despite containing millions of individual objects, the asteroid belt's total combined mass is surprisingly small, less than 4% of Earth's moon. This limited mass represents one of the most significant clues about the belt's formation, definitively disproving earlier theories that it might be the remnant of a shattered planet. Instead, the modest total mass indicates that the region never accumulated enough material to form a proper planet in the first place, pointing toward alternative formation scenarios. Asteroids within the main belt display significant compositional diversity, providing a crucial window into the material distribution of the early solar system. Most asteroids are composed primarily of rocky materials, often containing significant amounts of silicates, carbon compounds, and sometimes metals like iron and nickel. Based on their spectral properties and presumed compositions, asteroids are classified into several taxonomic types, with the main categories being S-type, stony, C-type, carbonaceous, and DP types, primitive, often containing organic compounds. The distribution of these different asteroid types throughout the belt is not random, but follows distinct patterns that reflect both their formation conditions and subsequent dynamical evolution. The compositional gradient observed across the asteroid belt, with certain types predominating in specific regions, provides significant evidence for theories about the belt's formation and evolution. S-type asteroids, which are relatively bright and contain metallic components, tend to dominate the inner portions of the belt, while darker, carbon-rich C-type objects are more prevalent in the middle to outer regions. This distribution supports models of planetary migration that suggest substantial mixing and reorganization occurred early in the solar system's history. Additionally, the preservation of these pristine materials from the solar system's birth makes the asteroid belt an invaluable resource for understanding the initial conditions from which our planetary system emerged. One of the earliest and most intuitive theories regarding the asteroid belt's origin was the failed planet hypothesis, which suggests that the belt represents material that never successfully coalesced into a full-size planet. According to this theory, in the early solar system, dust and rock circling the sun were gradually pulled together by gravity to form planets throughout the system. However, in the region between Mars and Jupiter, this process was disrupted, preventing the formation of a terrestrial planet similar to Earth or Mars. While this basic premise remains accepted, our understanding of the specific mechanisms involved has evolved substantially over time. The gravitational influence of Jupiter played a decisive role in preventing planet formation in the asteroid belt region. As Jupiter formed and grew into a massive gas giant, its powerful gravitational field began to exert significant influence on neighboring regions of the solar system. This gravitational perturbation increased the relative velocities of planetesimals, the building blocks of planets, in the area that would become the asteroid belt. Rather than gently accreting onto one another to build progressively larger bodies, these planetesimals began to collide at speeds too high for successful merging. Instead of fusion, these energetic impacts resulted in fragmentation, creating a scenario where material was being broken apart faster than it could accumulate. This disruptive process prevented the formation of a planet and established the fragmented region we now recognize as the asteroid belt. Evidence supporting this theory comes from the total mass of the asteroid belt, which is substantially less than would be expected for a fully formed planet. The entire belt contains less mass than Earth's moon, only about 4% of lunar mass, far too little to have ever constituted a proper planet. This modest mass aligns perfectly with the theory that the region represents material that was prevented from accumulating, rather than the remains of a once intact world. The size distribution of objects within the belt also supports this view, showing patterns consistent with fragmentation processes rather than catastrophic destruction of a single large body. A competing theory that once had significant support proposed that the asteroid belt might represent the remains of a planet that formed successfully but was later destroyed. According to this scenario, a planetary body might have developed in the region between Mars and Jupiter early in the solar system's history, only to be subsequently shattered by a catastrophic collision with another large object or torn apart by tidal forces from Jupiter. This dramatic explanation for the belt's origin captured the imagination of scientists and the public alike, but has gradually lost scientific support as more evidence has accumulated against it. The primary challenge to this theory comes from mass considerations. If a planet had formed and then been destroyed, we would expect to find a much greater total mass of material in the current asteroid belt than we actually observe. The modest mass of the belt, less than 4% of Earth's moon, is inconsistent with the remains of a shattered planet. Additionally, if such a catastrophic event had occurred, we would expect to find evidence in the composition and orbital characteristics of the resulting fragments. However, the diverse compositions and relatively ordered orbital structure observed in the asteroid belt align better with objects that never fully accreted into a planet, rather than the aftermath of a planetary explosion. While the destroyed planet theory has largely been abandoned by the scientific community, it did contribute to our understanding by prompting more detailed investigations into the asteroid belt's characteristics. As astrophysicist Sean Raymond of the Laboratory of Astrophysics of Bordeaux noted, the idea that maybe there was a planet in the asteroid belt and it got blown to smithereens has been largely disproven by subsequent research. The current scientific consensus strongly favors the failed planet hypothesis, with the asteroids representing planetesimals that never successfully combined into a larger body due to Jupiter's gravitational influence. A more recent and sophisticated theory for the asteroid belt's formation is the Grand Tack model, which incorporates the effects of planetary migration during the solar system's early history. According to this model, after Jupiter and Saturn formed, they did not immediately settle into their current orbits, but instead underwent significant migration. Jupiter initially moved inward toward the Sun, followed by Saturn. When the two planets came close enough to establish a specific orbital resonance, their inward movement halted, and they subsequently reversed course, moving outward until reaching their present positions. This dynamic orbital dance had profound implications for the asteroid belt region. As Jupiter migrated inward, its powerful gravity would have scattered or ejected much of the original material in the asteroid belt region, effectively emptying it. Then, as Jupiter and Saturn reversed direction and moved outward, they could have repopulated the region with material from both the inner and outer solar system. This complex migration pattern explains several observed features of the asteroid belt that are difficult to account for with simpler models. In particular, it helps explain the current taxonomic distribution of asteroid types throughout the belt, with different compositions predominating at different distances from the Sun. The Grand Tack model also provides a mechanism for delivering water-rich material from the outer solar system to the inner regions, potentially explaining Earth's water abundance. Recent research has further refined our understanding of Jupiter and Saturn's role in shaping the asteroid belt. A 2023 study published in Scientific Reports demonstrated that chaotic excitation generated by a near-resonant configuration of Jupiter and Saturn could create the conditions necessary for both terrestrial planet formation and the asteroid belt's current state. Computer simulations showed that this mechanism could typically deplete a massive disk beyond approximately 1.5 AU on a relatively short timescale of 5 to 10 million years. The resulting simulated system successfully reproduced not only the current orbits and masses of Venus, Earth, and Mars, but also explained the asteroid belt's orbital structure, small mass, and taxonomic diversity. This research represents a significant advancement in unifying our understanding of inner solar system formation processes. The story of the asteroid belt begins with the formation of the solar system itself, approximately 4.6 billion years ago. The solar system emerged from a large rotating cloud of gas and dust, known as the solar nebula, which began to collapse under its own gravity. As this cloud collapsed, it flattened into a spinning disk with the proto-sun at its center. This protoplanetary disk contained all the material that would eventually form the planets, moons, asteroids, and other objects in our solar system. The composition of this disk varied with distance from the central star, with more refractory materials dominating the inner regions and more volatile substances being more prevalent in the outer reaches. Within the first million years of solar system history, the particles within this disk began to collide and stick together, gradually forming larger aggregates called planetesimals. This process, known as accretion, proceeded at different rates throughout the disk, influenced by local density, temperature conditions, and distance from the forming sun. In the region that would become the asteroid belt, planetesimals were forming and beginning to grow through further collisions and gravitational attraction. However, this region would soon experience disruptive influences that would prevent these objects from following the same evolutionary path as the planetesimals in neighboring regions that would eventually become the terrestrial planets. The composition of the initial disk in the asteroid belt region would have included a mixture of rocky materials, metals, and some volatile compounds. This compositional profile is preserved in the diverse asteroid types we observe today. The early disk was much more massive than the current asteroid belt, containing perhaps 1,000 to 10,000 times more material than presently exists in the region. This substantial initial mass would later be dramatically reduced through various dynamical processes, leaving behind only a small fraction of the original material as the asteroid belt we observe today. The single most influential event in the asteroid belt's formation history was the emergence of Jupiter, the solar system's largest planet. Jupiter formed relatively quickly in astronomical terms, reaching much of its current mass within the first few million years of solar system history. As a gas giant, Jupiter's formation began with the accretion of a solid core, followed by the rapid accumulation of gas from the surrounding protoplanetary disk. Once Jupiter reached a critical mass of about 10 Earth masses, it began to gravitationally capture gas at an accelerating rate, quickly growing to become the dominant gravitational influence in the outer solar system. Jupiter's formation had immediate and profound effects on the developing asteroid belt region. The growing gas giant's powerful gravitational field began to perturb the orbits of the planetesimals in the neighboring asteroid belt region. These perturbations increased the relative velocities of objects in the belt, causing their orbits to become more eccentric and inclined. As orbital eccentricities increased, planetesimals began to cross each other's paths at higher relative speeds. This crucial change transformed what had been gentle constructive collisions that promoted growth into energetic, destructive impacts that caused fragmentation rather than accretion. The timescale of this disruptive process was relatively short in astronomical terms. According to current models, it is estimated that approximately 99.9% of the asteroid belt's original mass was lost within the first 100 million years of solar system history. This dramatic depletion occurred through a combination of fragmentation and ejection. The most recent research suggests that the chaotic excitation generated by Jupiter and Saturn's gravitational influence could typically deplete the region beyond 1.5 AU on a timescale of just 5 to 10 million years, highlighting the efficiency of this disruptive process. Following the initial period of disruption and mass depletion, the asteroid belt entered a phase of slower evolution, characterized by continued collisional processing and dynamical sorting. While the most dramatic changes to the belt occurred within the first 100 million years, the region has continued to evolve throughout the solar system's 4.5 billion year history. This extended evolution has shaped many of the features we observe in the contemporary asteroid belt, including its current mass distribution, the prevalence of asteroid families, and the complex orbital structure of its constituent objects. Collisions between asteroids remain an ongoing process, though occurring at a much reduced rate compared to the early solar system. These impacts continue to modify the size distribution of objects in the belt by breaking larger bodies into smaller fragments. Evidence of this ongoing collisional evolution has been directly observed by modern telescopes. For instance, the Hubble Space Telescope has witnessed the disintegration of asteroid P-2013-R3 into 10 smaller pieces, with the fragments drifting apart at approximately 1 mile per hour. Similarly, Hubble has observed the aftermath of high-velocity collisions between asteroids, revealing complex X-shaped patterns of debris consistent with head-on impacts occurring at speeds 5 times faster than a rifle bullet. These observations confirm that the asteroid belt continues to evolve through collisional processes even in the present era. Beyond physical collisions, the asteroid belt is also subject to more subtle dynamical effects that gradually modify asteroid orbits. Resonance phenomena, particularly those associated with Jupiter, can cause asteroids to slowly migrate out of the main belt over long timescales. The Yarkovsky effect can also modify asteroid orbits over millions of years, particularly for smaller objects. These processes ensure that the asteroid belt remains a dynamically active region, continuing to lose mass, albeit at a much slower rate than during its formative period. The asteroid belt we observe today thus represents a dynamic equilibrium between formative processes that occurred billions of years ago, an ongoing evolution that continues to reshape this fascinating region of our solar system. The asteroid belt contains a diverse array of object types that vary significantly in their composition, reflecting the heterogeneous nature of the protoplanetary disk from which they formed. Scientists classify asteroids into several taxonomic groups based on their spectral properties, which provide clues about their surface composition and internal structure. The most common classification system identifies several main types, including S-type, stony, C-type, carbonaceous, M-type, metallic, and various other categories such as D-type and P-type asteroids. This compositional diversity serves as a crucial record of the conditions that existed in different regions of the early solar system. S-type asteroids, which dominate the inner portion of the asteroid belt, are composed primarily of silicate materials and sometimes contain metallic iron-nickel. Their composition suggests they formed in regions of the protoplanetary disk where temperatures were relatively high, causing volatile compounds to vaporize while leaving behind refractory materials. These objects share compositional similarities with ordinary chondrite meteorites that occasionally fall to Earth, providing direct samples of this asteroid type for laboratory analysis. The prevalence of S-type asteroids in the inner belt aligns with thermal models of the protoplanetary disk, which predict higher temperatures in regions closer to the Sun. C-type asteroids, which are more common in the middle and outer regions of the belt, contain significant amounts of carbon compounds and water-bearing minerals. Their darker surfaces and carbon-rich composition indicate they formed in cooler regions of the protoplanetary disk, where volatile compounds could remain stable. These asteroids are particularly valuable for understanding the distribution of water and organic compounds in the early solar system. The presence of water-bearing minerals in C-type asteroids provides evidence for the transport of water from the outer solar system to the inner regions, potentially explaining the origin of Earth's oceans and supporting the grand TAC model of planetary migration. The current distribution of different asteroid types throughout the belt provides compelling evidence for large-scale mixing processes during the solar system's early history. According to simple models of protoplanetary disk evolution, we would expect to see a smooth compositional gradient from the inner to the outer asteroid belt, with more processed, heat-altered materials closer to the Sun and more primitive, volatile-rich materials farther away. While this general trend is observed, the actual distribution is considerably more complex, with different asteroid types often interspersed throughout the belt, rather than being strictly segregated by distance. This complex distribution pattern supports models involving significant radial mixing, where material from different regions of the protoplanetary disk was transported and redistributed during the solar system's formation. The grand TAC model provides a mechanism for this mixing, as Jupiter's inward then outward migration would have scattered material throughout the solar system. As Jupiter moved inward, it would have pushed some inner solar system material outward, while also drawing some outer solar system material inward. Then, as Jupiter reversed course and moved outward, it would have redistributed this material again, resulting in a mixed population of asteroid types throughout the belt. Recent research has further refined our understanding of this process. A 2023 study demonstrated that chaotic excitation generated by Jupiter and Saturn could create conditions that explain not only the current structure of the asteroid belt, but also its taxonomic distribution. The model successfully reproduced the observed pattern of S-type, C-type, and DP-type asteroids throughout the belt, providing strong support for the role of giant planet migration in shaping the solar system's architecture. This mixing of material from different regions also has implications for terrestrial planet formation, particularly regarding the delivery of water and organic compounds to Earth during its formation. The presence and distribution of water and organic compounds in the asteroid belt provide crucial information about conditions in the early solar system and the processes that delivered these essential materials to the inner planets. Many C-type and D-type asteroids contain significant amounts of water, either in the form of hydrated minerals or potentially as subsurface ice. This water content varies throughout the belt, with generally higher abundances in the outer regions, consistent with the temperature gradient that existed in the protoplanetary disk. The distribution of water-bearing asteroids supports models involving the inward transport of water-rich material from beyond the snowline, the distance from the Sun, where water could exist as ice in the early solar system. According to recent research, the chaotic excitation model involving Jupiter and Saturn created conditions that allowed for effective water delivery during the first 10-20 years of Earth's formation. This finding helps explain one of the most fundamental questions in planetary science: how Earth acquired its water, despite forming in a region of the protoplanetary disk, where water would have been primarily in vapor form. Beyond water, many asteroids also contain organic compounds, including complex carbon molecules, that represent potential chemical precursors to life. The presence of these compounds in certain asteroid types provides evidence for the synthesis and preservation of organic materials in the early solar system. The delivery of these compounds to Earth through asteroid impacts may have played a crucial role in establishing the conditions necessary for life to emerge. By studying the organic content of different asteroid types throughout the belt, scientists can reconstruct the chemical evolution of the protoplanetary disk and better understand the processes that distributed these essential building blocks throughout the solar system. The current structure of the asteroid belt is characterized by a series of gaps and concentrations that reveal the ongoing influence of gravitational dynamics on this region. These features, known as Kirkwood gaps, are areas within the belt where asteroids are notably absent or scarce. The gaps correspond to specific orbital resonances with Jupiter, where an asteroid would complete a precise fraction or multiple of Jupiter's orbital period. For example, there are prominent gaps at locations where asteroids would orbit the Sun 3 times for every 1 Jupiter orbit, or 5 times for every 2 Jupiter orbits. These resonance effects demonstrate the continuing influence of Jupiter on the asteroid belt's evolution. When an asteroid's orbit falls into one of these resonance positions, it experiences regular, periodic gravitational tugs from Jupiter. Over time, these repeated gravitational influences amplify the eccentricity of the asteroid's orbit, eventually causing it to cross the paths of other planets or the Sun itself. This process effectively removes objects from these specific orbital positions, creating the observed gaps. The presence and precise positions of these gaps provide strong evidence for the role of orbital dynamics in shaping the asteroid belt throughout solar system history. Beyond creating gaps, resonances also contribute to the formation of asteroid families. Groups of asteroids that share similar orbital characteristics and are believed to have originated from the fragmentation of a single larger parent body. When a collision occurs and fragments a larger asteroid, the resulting pieces initially share similar orbits. Over time, these fragments are influenced by various gravitational and non-gravitational forces, causing their orbits to disperse in characteristic patterns. By studying these patterns, scientists can reconstruct past collisional events and trace the evolutionary history of different regions within the asteroid belt. Asteroid families provide crucial insights into the collisional processes that have shaped the belt throughout its history. These families are identified as clusters of asteroids with similar orbital elements and often similar spectral properties, suggesting a common origin. More than 120 asteroid families have been identified to date, representing generations of collisional breakups spanning billions of years of solar system history. By studying these families, scientists can reconstruct the frequency and nature of impacts in different regions of the belt and at different times. The age distribution of asteroid families reveals that collisional processes have operated continuously throughout solar system history, though at varying rates. Some families are extremely ancient, dating back more than 2 billion years, while others formed within the last few million years or even more recently. The Charon family, for example, formed approximately 5.8 million years ago from the breakup of a 40-kilometer diameter parent body, making it one of the youngest identified families in the belt. Direct observations of recent breakup events, such as the disintegration of asteroid P-2013-R3 witnessed by the Hubble Space Telescope, provide real-time evidence of the ongoing collisional evolution in the belt. The compositional characteristics of asteroid families also provide valuable information about the internal structure of their parent bodies. When a large asteroid is fragmented by an impact, material from different depths is exposed and distributed among the resulting family members. By studying the spectral properties of these fragments, scientists can infer the compositional layering that existed within the parent body prior to its disruption. This information helps constrain models of thermal evolution and differentiation processes in early solar system objects, providing insights into the conditions that existed as these bodies formed and evolved. Meteorites represent direct physical samples of asteroid belt material that can be analyzed in terrestrial laboratories, providing unparalleled insights into the composition and history of these ancient objects. Most meteorites originate from the asteroid belt, arriving on Earth after being ejected from their parent bodies through collisions and subsequently crossing Earth's orbit. The diverse types of meteorites reflect the compositional variety of their asteroid sources, with different classes corresponding to different regions and formation conditions within the early solar system. Chondrites, the most common type of meteorites, contain small spherical inclusions called chondrules that formed during the earliest stages of solar system evolution. These primitive meteorites have experienced minimal alteration since their formation approximately 4.56 billion years ago, making them valuable time capsules of early solar system conditions. The elemental and isotopic compositions of chondrites provide crucial constraints on the chemical makeup of the protoplanetary disk, while their physical structures offer insights into the accretion processes that form the first solid bodies in our solar system. Chondrites represent more evolved meteorite types that experienced significant melting and differentiation within their parent bodies. These meteorites formed when asteroids grew large enough for their interiors to melt, allowing heavier elements like iron and nickel to sink toward the center, while lighter silicate materials floated toward the surface. Iron meteorites are believed to originate from the cores of differentiated asteroids that were subsequently shattered by impacts, exposing their metallic interiors. By studying these different meteorite types, scientists can reconstruct the geological evolution of asteroids throughout solar system history, from their initial accretion to subsequent episodes of heating, melting, and fragmentation. Advanced computer simulations have dramatically improved our understanding of the processes that shape the asteroid belt during solar system formation. These sophisticated models incorporate multiple physical factors, including gravitational interactions, collisional dynamics, gas drag from the protoplanetary disk, and radiative effects to reconstruct the complex evolution of the early solar system. By comparing the outcomes of these simulations with the observed properties of the current asteroid belt, scientists can test different formation scenarios and constrain the conditions that must have existed in the primordial solar system. Recent simulations focused on the role of giant planet migration have been particularly successful in reproducing the observed characteristics of the asteroid belt. A 2023 study published in Scientific Reports demonstrated that chaotic excitation generated by a near-resonant configuration of Jupiter and Saturn could create conditions that explain both terrestrial planet formation and the current state of the asteroid belt. These simulations showed that this mechanism could typically deplete a massive disk beyond approximately 1.5 AU on a timescale of 5 to 10 million years, consistent with the observed low mass of the current belt. Importantly, the resulting simulated systems successfully reproduced not only the current orbits and masses of Venus, Earth, and Mars, but also explained the asteroid belt's orbital structure, small mass, and taxonomic diversity. Beyond explaining the asteroid belt's formation, these simulations have also addressed other crucial aspects of solar system evolution. The same models that successfully reproduce the asteroid belt's characteristics also provide explanations for the timing of Earth's moon-forming impact, occurring after a median of approximately 30 to 55 million years, and the effective delivery of water to Earth during its first 10 to 20 million years of formation. This convergence of multiple lines of evidence provides strong support for these models and demonstrates the interconnected nature of different aspects of solar system formation. Direct observations from space telescopes and dedicated missions have provided crucial empirical data that complement theoretical models of asteroid belt evolution. The Hubble Space Telescope has been particularly valuable in documenting ongoing processes within the belt. Hubble has observed several significant events, including the disintegration of asteroid P-2013-R3 into multiple fragments, the aftermath of high-velocity collisions producing X-shaped debris patterns, and asteroids with unusual comet-like tails of dust. These observations provide direct evidence of the continuing collisional evolution of the asteroid belt and the diverse physical processes operating within this region. Specialized asteroid missions have yielded even more detailed information about specific objects within the belt. NASA's Dawn mission, for example, conducted comprehensive studies of Vesta and Ceres, the two largest objects in the asteroid belt. The data returned from Dawn revealed that Vesta is a differentiated body with a core mantle crust structure similar to terrestrial planets, supporting models of early heating and melting in large planetesimals. Ceres, by contrast, was found to contain significant amounts of water, ice, and hydrated minerals, with evidence for past subsurface liquid water and potentially ongoing geological activity. These findings highlight the diversity of evolutionary pathways followed by different objects within the asteroid belt and provide ground truth for models of early solar system thermal evolution. Sample return missions represent the latest frontier in asteroid belt research, bringing actual material from specific asteroids back to Earth for laboratory analysis. Japan's Hayabusa and Hayabusa 2 missions returned samples from the near-Earth asteroids Itokawa and Ryugu, respectively, while NASA's OSIRIS-REx mission collected material from asteroid Bennu. Although these target asteroids orbit near Earth rather than in the main belt, they are believed to have originated in the belt before being gravitationally scattered into their current orbits. The samples returned by these missions provide unprecedented insights into the composition and history of their parent bodies, including evidence for aqueous alteration, organic compounds, and complex geological histories that reflect the diverse conditions present during solar system formation. Research on our own asteroid belt has significant implications for understanding the formation of planetary systems around other stars. The processes that shaped our solar system, including the role of giant planets in sculpturing inner system architecture and the influence of resonances on small body populations, are expected to operate in exoplanetary systems as well. By developing a comprehensive understanding of our own system's history, scientists can better interpret the limited observational data available for distant planetary systems and predict their likely evolutionary pathways. Observations of debris disks around other stars provide the closest analog to our asteroid belt in exoplanetary systems. These disks, composed of dust and larger bodies orbiting at various distances from their host stars, represent either the early stages of planetary system formation or the aftermath of collisional evolution, similar to our own asteroid belt. The structure of these debris disks, including gaps and concentrations similar to those observed in our asteroid belt, offers evidence for the presence of unseen planets that gravitationally shape these regions. By applying the lessons learned from studying our own asteroid belt, astronomers can infer the properties of these exoplanets and reconstruct the formation history of these distant systems. The diversity observed in exoplanetary system architectures suggests that the specific pathway followed by our solar system represents just one of many possible evolutionary trajectories. Some systems appear to have undergone more dramatic planetary migration than our own, while others show evidence for less disruption of their primordial structure. By comparing these different outcomes with detailed models of our own solar system's formation, scientists can identify the key factors that determine a system's evolutionary path. The asteroid belt thus serves not only as a window into our solar system's past, but also as a valuable point of comparison for understanding the full spectrum of planetary system formation processes operating throughout the galaxy. The asteroid belt stands as one of the most valuable cosmic fossil records in our solar system, preserving evidence of processes and conditions that existed during the formation of our planetary neighborhood 4.5 billion years ago. Unlike the planets, which have undergone extensive geological evolution that has erased much of their primordial character, many asteroids represent relatively unaltered remnants from the solar system's earliest epochs. Their compositions, orbital distributions, and physical characteristics collectively tell a complex story of accretion, disruption, and dynamical evolution that shaped not only the belt itself but the entire inner solar system. The relationship between the asteroid belt and solar system formation is multifaceted and bidirectional. On one hand, the conditions present during solar system formation, including the gravitational influence of the forming giant planets and the compositional gradient of the protoplanetary disk, directly determine the asteroid belt's initial properties and subsequent evolution. On the other hand, the current state of the asteroid belt provides crucial constraints on models of solar system formation, serving as a testbed for theories about planetary migration, accretion processes, and dynamical evolution. The successful reproduction of the belt's observed characteristics represents a necessary condition for any comprehensive model of solar system formation. Recent research has substantially advanced our understanding of this relationship, demonstrating how specific mechanisms such as the chaotic excitation generated by Jupiter-Saturn interactions can explain both the current state of the asteroid belt and other key features of our solar system. These advances highlight the interconnected nature of solar system formation processes and underscore the value of the asteroid belt as a window into our cosmic past. As observational capabilities continue to improve and computational models become increasingly sophisticated, our understanding of the asteroid belt's role in solar system formation will undoubtedly continue to evolve, revealing new insights into the processes that shaped our cosmic home and potentially countless other planetary systems throughout the universe?